All right, today we're diving into the work of a physicist who's, well, a bit of a maverick. He tackles the biggest problems in the universe with a perspective that is so fresh, some people would say it's impossible. His name is Professor Frederic Schuller. And look, that's not me being dramatic. That's a direct quote from people who have seriously studied his work. It really gets to the heart of how he thinks. He just looks at the foundations of physics, the stuff we all take for granted, and asks, what if we're starting in the completely wrong place? And there it is. The central, absolutely mind-bending claim. He didn't assume gravity, he didn't postulate it, he derived it. He started with the physics we know about light, about electricity and magnetism, and from that, and only that, he showed that gravity, exactly as Einstein described it, has to exist.
To really get what a huge deal this is, you have to see the contrast. The standard way of doing things, the view in all the textbooks, is that you need two separate sets of rules, one for matter and one for gravity. You just kind of assume they both exist. But Schiller's view is totally different. He says, no. If you just define the rules for matter correctly, the rules for gravity just pop out as a necessary consequence.
Okay, so section 1, the impossible derivation.
So how on earth is this possible? The logic is actually beautifully simple. It's a three-step process. First, you start with a theory of matter that we know works, something solid like electromagnetism. Step 2, and this is the absolute key, you make one single demand. The theory has to be predictive. The result? It's just astonishing. For that to be true, the space-time that the matter exists in must obey Einstein's equations. But what does he actually mean by predictive? You can think of it like this. A theory is predictive if, once you know everything about the system right now, you can calculate everything about it a moment later. No cheating, no surprises. You don't need some new information from the future to figure out what happens next. Matter and space-time have to evolve together in perfect lockstep from the exact same set of starting conditions. And this just shows the incredible power of that one demand. By just insisting on predictivity, Einstein's equations aren't an option anymore. They become a mathematical necessity. It is literally the only way that space-time can evolve in a way that's consistent with the matter that lives inside it.
All right, section 2, an engineer's tool for quantum mechanics.
Now, Schuller's unique cross-disciplinary way of thinking doesn't stop with gravity. To get our heads around his approach to quantum mechanics, we have to ask a question that sounds like the beginning of a really weird joke. What does building a robot have to do with this strange, fuzzy world of quantum particles? Well, as it turns out, a whole lot. Schuller got inspired by an idea from, of all places, engineering. It's called the Port-Hamiltonian approach. Imagine you're an engineer building a robot arm or designing an electrical grid. You absolutely need to know how energy is flowing, in, out, and between all the different parts. So they model this system with ports, where these quantities, like energy, get exchanged. And here is Schuller's big aha moment. He realized that in classical systems, like robots, you're tracking the flow of energy. But in quantum systems, something else is flowing around. Probability. So he took this powerful engineering tool and adapted it, using it to describe the flow of probability in quantum mechanics. So why is this so important? Because Schuller is famous for wanting to turn what he calls just talk into actual precise mathematics. You know, phrases like, when you measure the particle, they sound fine, but mathematically, they're kind of vague. This new approach gives physicists a rigorous language to actually calculate and describe what's happening during a measurement. It takes it out of the realm of just talk and turns it into real, hard formalism. Okay, this brings us to section 3, the power of modest ideas. So these two examples, they really point to a deep philosophy that runs through all of Professor Schuller's work. It's all built on the surprising power of simple, well-chosen ideas. And this quote, it just says it all. Notice he says therefore, not in spite of. For Schuller, being modest isn't a weakness. It's the very reason an idea has a chance to work. Grand, complicated theories with 10 new assumptions, they usually just collapse under their own weight. You can actually distill his whole philosophy down into a few key principles. First, start with one good idea, not 10. Then, take the theories we already have, the ones that work, seriously. From there, you let the problem itself tell you where to go next. And you always focus on generalizing the core concepts, the big ideas, not just playing games with the equations. You trust the hints that nature is giving you. And this way of thinking isn't just for his research. It's the secret sauce in his award-winning teaching.
His online courses are legendary, and for a good reason. He builds entire fields of physics and math from the absolute ground up. If he's going to teach you differential geometry, he doesn't start with curves and surfaces. He starts with propositional logic, with set theory. He makes sure every single brick in the wall is resting on a rock-solid foundation.
Which brings us to our final section, physics as a masterpiece.
You know, when you put it all together, his derivation of gravity, his fresh take on quantum mechanics, his whole philosophy of starting with modest, rigorous ideas, a really beautiful picture of physics starts to emerge. He shows us that physics isn't just a jumble of different theories. It's a single, coherent masterpiece where every single piece, from logic all the way up to gravity, interlocks perfectly, like the details in a Da Vinci painting.
And that's really the big takeaway here. The point isn't just to memorize a list of facts and equations. The real goal is to see the entire structure, to really understand how and why it all fits together, and to just appreciate the incredible beauty and logic of the universe it describes. And that leaves us with a final, really inspiring thought. If starting with just one simple, modest idea can unlock a whole new understanding of gravity or of quantum mechanics, it really makes you wonder, doesn't it? What other hidden masterpieces are just waiting out there, ready to be revealed by the next modest idea?